Hey guys, how's it going? I'm gonna miss you guys so much this week, but we have tons of stuff to do. You guys have your semester exam next week. And so I want to make sure that we are as productive as possible. So if you will, please, go ahead and open up your packet that you got from the sub today. If you have not received it yet, then go ahead and pause this video and let's get that passed out, please. Hold on, my thing's not working. Go figure. Maybe. Okay, so the basic overview for what the plan is for this week is we have kind of like two big things that need to happen. The first one is that we have 3 different mini lessons. And the second one is that you have a pretty lengthy semester exam review. So for first period, it's going to be broken up a little bit differently than 7th period. So I'm trying to make like several shorter videos so that they can be split up appropriately. We're going to start class today with one of the mini lessons. Basically, just because of COVID and everything else, we're a little bit behind where we would normally be. And so rather than giving us tons of stuff in second semester to have to make up from this semester, we're just going to kind of power through. They're not big topics, so it shouldn't be too hard. So the first one we're going to do is L'Hôpital's rule. So if you'll get this packet and then turn like several pages back to where L'Hôpital's rule starts, we're going to do this mini lesson first. Okay? So take a look at that for me, please. I know we haven't looked at limits in a while, but L'Hôpital's rule is one of your limit properties. So we're going to do this first little warm-up question here. It's the limit as x approaches 0 of x plus 6 over x squared minus 1. So if you remember, okay, we always try when we're doing limits to substitute first. So I would do 0 plugged in. I'd have 0 plus 6 on top, 0 minus 1 on bottom, and then 6 divided by -1, boom, -6. Easy. Okay, when you get to number 2, though, you try to plug in 3. Okay, you get 3 squared, which is 9. 9 minus 9 on top. But then you get 3 minus 3 on bottom, and it's like, uh-oh, didn't work. Okay, so another method that we talked about to fix limits, if you can't directly substitute, is that you can try factor cancel, okay, which is our second strategy on this list here. So if I rewrite this limit as x approaches 3 in factored form, my x squared minus 9 is going to split up into x plus 3 and x minus 3. I have an x minus 3 on bottom. And then you'll notice that your x minus 3s are going to cancel out. And then the leftover equation, I can take my 3, bop it in here. 3 plus 3 is 6. And the limit still exists, and we can work it out by factor cancel. So just let's review real quick what this means. This means that there is a removable discontinuity, which is a hole, at x equals 3, where hole is at y equals 6. So basically you have this situation where technically there's not a dot there. It is a discontinuity. However, the limit still exists because I was able to fix that limit, okay? So another way for you to check and see if a limit exists is using this rule that I'm about to teach you, which is called L'Hôpital's rule. Okay, factor cancel can fix some limits, but L'Hôpital's rule can fix all limits, okay? Well, okay, let me rephrase that. All limits that exist. Okay, if a limit doesn't exist, nothing's going to fix it, right? Okay, not factor cancel, not L'Hôpital's rule. But if a limit exists, L'Hôpital's rule can fix it. So let's go over what L'Hôpital's rule is. It says for 2 differentiable functions, f and g, if the limit as x approaches a of f of x is 0, okay, that would be what I have here on the top, and the limit as x approaches a of g of x is 0, then the limit as x approaches a of f over g results in an indeterminate form, which means that you got 0 on top and 0 on bottom. Whenever that happens, you're allowed to use this rule, which says that this limit is equal to the limit as x approaches a of the derivative of the top divided by the derivative of the bottom. So if your top limit and your bottom limit both come out to be 0, what you're allowed to do is take the derivative of the top and the bottom and then try the limit again, okay? So let's look at some conditions for the theorem. This theorem only applies when f and g are differentiable functions. Okay, so we have to make sure they're both differentiable. And then also your limit as x approaches a of f has to be 0 and g has to be 0. Okay, now you cannot write that the limit equals 0 over 0 because what did we say up at the top? Okay, that's an indeterminate form, which basically means it's like you're going to math jail, okay? Indeterminate form. You are not allowed to put that something is equal to something divided by 0. It doesn't make sense. 0 divided by 0 doesn't make sense. It's just never allowed. Okay, so what we're going to do instead is show the limits are equal to 0 separately, okay? So take a look at number 1. Okay, we have x cubed minus 8 over x minus 2, and our limit is approaching 2. So the first thing that I would do is just make sure my functions are differentiable. Okay, well, x cubed minus 8 is a cubic function. Okay, same thing for x minus 2, that's a linear function. So those are both good to go. So are they differentiable? Yes. Okay, step 2, I need to check the limits are equal to 0 separately. So I'm going to check the limit as x approaches 2 of the top function. I'd get 2 cubed, which is 8, minus 8, which gives me 0. Okay, that was for the top. Then I would check the same thing for the bottom. So I would do the limit as x approaches 2 of x minus 2. Remember, you're just substituting. Take your 2, plug it in right there. That's 2 minus 2, which gives me 0. So the limit for the top came out to be 0. The limit for the bottom came out to be 0. Then that means that I'm allowed to rewrite my limit as x approaches 2 of f prime of, oops, I guess I might as well just take the derivative. Okay, but it would be f prime of x over g prime of x, so we're going to take the derivatives. So take a look at the top equation here. X cubed minus 8, derivative of that is 3x squared. 8 is a constant, derivative of a constant is 0. On the bottom, we have an x minus 2. Derivative of x minus 2 is just going to be a 1. And then again, minus 2, derivative goes to 0. Okay? Then from there, you can retry the limit. So I would take my x approaching 2 here, bop it back into the limit. I would have 3 times 2 squared. 2 squared is 4. 4 times 3 is 12. So what that means is my limit as x approaches 2 does still exist. Even though it's not a continuous function, okay, it's a whole, which means that the limit from both sides is approaching a y value of 12. Okay, go down to number 2. Number 2 says we have the limit as x approaches 0 of cosine x minus 1 over 6x. Remember, I'm going to check both of these functions to make sure that they're continuous and differentiable separately, which they are. Cosine just does this all day. 6x is a straight line, so those are both good to go. So the first thing that I'm going to do is I'm going to check the top and the bottom limits separately. So I'm going to check the limit as x approaches 0 of cosine x minus 1. Well, that'd be cosine of 0 minus 1. Cosine of 0 is 1 minus 1. That does give me 0. Then I'm going to check the limit for the bottom. Well, my bottom function is just a 6x. So the limit of 6x as x approaches 0, I would have plug in the 0, 6 times 0, which is 0. So my top limit came out to be 0. My bottom limit came out to be 0. Then that means that I can now use L'Hopital's rule on this guy. So I'm going to retry my limit as x approaches 0, but I'm going to take the derivative of the top and the bottom. So my top function is a cosine x. So snow cone, snow cone. Okay, I'm going down the list from cosine. So cosine is here. Derivative is going to be negative sine x. And then 1 is a constant, and the derivative of minus 1 is going to give me 0. So that means I'm just going to leave it in negative sine x on the top. Derivative on the bottom is 6 of my 6x is just going to be a 6. And then remember, the reason that we did this is because it was 0 over 0, but now I get to try the limit a second time. So when I plug in 0 here, I'm going to have the negative sine of 0 over 6. Sine of 0 is 0, but 0 divided by 6 is a number. That's 0. Okay, this is not an indeterminate form anymore. Okay, that is not indeterminate form. Okay, and then one easy way to remember it, if you like really cheesy things, okay, is that it is okay to get 0 on the top. That's going to give you 0. Okay, but no, you can't get 0 on the bottom. That means your limit is a DNE. Okay, but then, okay, here's the new one. I think I showed y'all this earlier. If it's 0 over 0, that means you can do more. Yeah. Okay. So if you get 0 over 0, you got to do more because that's the indeterminate form and you can't make a conclusion about whether or not the limit exists. Okay. So no, you don't have a limit if 0 is on the bottom. It's okay to have a 0 on the top. 0 over 0 though, baby, you better do more. Okay. All right, turn the page when you're ready. And then substitute if they need me to, if I'm going too fast, just pause the video, no problem. Okay, we're turning the page here. All right, so our next question, we have the sine of 5x over 3x. So my first step would be for me to plug in the limit as x approaches 0 to the top and the bottom separately. So I'm going to start off by doing the limit as x approaches 0 of sine 5x. Well, when I plug my 0 in here, that's the sine of 5 times 0, which is 0. And the sine of 0 is in fact 0. Then I check my bottom. I want the limit as x approaches 0 of 3x. Obviously, plug in 0 to that. 3 times 0 is 0. So I see that both my top and my bottom limits gave me 0 separately. Then I'm allowed to apply L'Hopital's rule. Now, when I take the derivative, okay, let's reapply our limit here. X approach 0. The bottom limit, 3x, the derivative is 3. Okay, super easy. On the top, you're going to need chain rule. So let's review what chain rule is. Chain rule is when you take the derivative of a function that has another function inside it. Okay, so for this, 5x is plugged inside sine. So that means I take the derivative of sine first, which is cosine, keep the 5x the same, and then multiply by the derivative of 5x, which is another times 5. And then from there, I'm going to reapply that limit and see if it works out. So we're letting x approach 0. So I would plug that in right there. So I would have the limit as, oh wait, I guess I don't have to write that anymore. I'd have the cosine of 5 times 0, which is 0 times 5 over 3. Cosine of 0 is 1. 1 times 5 is 5. So 5/3 is the answer. So that means that even though my function is not continuous, I have a removable discontinuity, which means that I do in fact still have a limit. Okay. All right, next question. Let's go to number 4. Okay, we have x approaching 0. I'm going to check both my limits separately. So first I'm going to let x approach 0 for the top function. Well, plug in 0, e to the 0 minus 1 is 1 minus 1, which is 0. Okay, then I check it for the bottom. Limit as x approaches 0 of 2x. Well, that'd be 2 times 0, which is 0. So I got 0 on top and on bottom. That means I got to do more, okay? So we're ready to take the limit again. Okay, and L'Hopital's rule says that the limit of two functions is equal to the limit of its two derivatives. So e to the x minus 1, okay, e to the x is its own derivative, and then minus 1 is a constant, so the derivative of 1 is just 0, it goes away. 2x on the bottom, I have a derivative that is 2. Then I'm going to let x approach 0, which means that I have e to the 0 over 2, which is 1/2. Okay, but remember, every time that you're working these limits out, you're trying to see if a limit that originally gave you a 0 on the bottom, if it actually exists, okay? So let's check the next one. We have the limit as x approaches 3 of e to the x, and then the limit as x approaches 3 of x minus 3. Okay, I'm going to plug in my 3 here first. 3 minus 3 gives me 0. So check. I can do L'Hopital's rule as that condition is met. Okay, but then when I go to check the other one, look what happens. Plug in a 3 to that, I get e to the 3. That's not 0. That means no L'Hopital's rule. Okay, L'Hopital's rule can't, I think I spelled that wrong. Oh no, that's right. Okay, no L'Hopital's rule. It has to be 0 over 0. Okay, I got e cubed over 0. That's a no, right? So that means this limit is a DNE. Okay, and that L'Hopital's rule was not able to fix that. Okay. All right, let's go down to number 6. Number 6, I have e to the x minus e to the 3 over x minus 3, limit as x approaches 3. So I'm going to do the top first, x approaching 3 on e to the x minus e to the 3. Well, when I plug my 3 in there, I get e to the 3 minus e to the 3, which does in fact give me 0. Check the other side. We want the limit as x approaches 3 of my bottom function, which is x minus 3. 3 minus 3 gives me 0, which means both of those gave me 0. That means it's a 0 over 0, do more type situation. Okay, but we have to take the derivative. So I'm going to reapply the limit here. E to the x minus, okay, so e to the x is its own derivative. Let's talk though about this e cubed. Okay, the derivative of e to the x is e to the x, but the derivative of e cubed is 0. Okay, think about why. E is just a number. E cubed is just a number. That means that this term is actually just a constant. And the derivative of any constant is 0. So that second part of that top subtraction just goes away. Same thing happens on the bottom. I had an x minus 3. Derivative of x is just a 1. And then when I reapply this limit, I just get e cubed on top over 1, which means that limit does still exist and it equals e cubed. Okay. All right, take a look at the next one, number 7. We have x approaching 0. So I'm going to plug that in top and bottom, check my limits. If you get 0 on top and on bottom, you can use L'Hopital's rule. So let's see if we can use it here. So limit as x approaches 0 of 2x squared would be 2 times 0 squared, which is 0. Okay, put a little check mark there. We got a 0 there. Okay, now I need to check it for the bottom. So the limit as x approaches 0 of e to the x minus 1 minus x. Remember, we're plugging in x approaching 0. So e to the 0 minus 1 minus 0. Well, e to the 0 is a 1. 1 minus 1 minus 0 is 0. Check. That means that L'Hopital's rule can potentially fix my limit. Now, what if I still get 0 on the bottom even after I tried to fix it? Well, then it could be that it's really a DNE, but we don't know until we find out. So let's see. Okay, here we go. We're taking the derivative of the top. So it's the limit as x approaches 0 again. 2x squared, the derivative is a 4x. E to the x, the derivative is still e to the x. Minus 1 is a constant, so that term is out of there. And then minus x, the derivative is a minus 1. Then I go to plug in my x approaching 0, and what do you notice happens again? Okay, I take my x approach 0, bop. 4 times 0 is 0. Plug it in on bottom. E to the 0 minus 1 is 1 minus 1, which is 0. Okay, that means that I'm going to have to do L'Hopital's rule again. Okay, so one more time, here's why. So I'm going to switch from my blue to my purple. When I check the top limit as x approaches 0 of 4x, I get 4 times 0, which is 0. Then I check the bottom limit. Limit x approach 0 of e to the x minus 1. I get e to the 0, which is 1, minus 1, which is 0. So L'Hopital's rule could go on forever. I mean, obviously, hopefully it doesn't. But as long as you're getting 0 over 0, you cannot make a conclusion until one of the pieces of the equation stops being a 0. Okay? So in this case, a second L'Hopital's rule ends up fixing it. Here's why. So on top, I'm trying the limit as x approaches 0 again. 4x, the derivative is just a 4. And then e to the x, the derivative is e to the x again. Minus 1 is now a constant, which means that its derivative is 0. And this limit is going to work out just fine. Okay, take your x approach 0, go and plug it in. You're going to get 4 divided by e to the 0, which is 4 divided by 1, which is 4. Okay, so it is possible for a L'Hopital's rule once to not be conclusive, but then you do it again and it could be conclusive that second time. Okay? All right. Turn the page. Ooh, good. Okay, we're almost done. Take a look at number 8. Number 8 looks kind of similar to that one that we just did. We're doing x approaching 4. We have ln x minus ln 4 over x minus 4. So I'm going to do the limit as x approaches 4 of the top function, which is ln x minus ln 4. Well, when I plug in a 4 to that, I'm going to have ln 4 minus ln 4. And we know that that's 0. Same thing on the bottom here. I'm going to do the limit as x approaches 4 of x minus 4. Well, that comes out to be 4 minus 4, which also gives me 0. So I got 0 over 0, even though I can't write it like that. Okay, that's the indeterminate form that tells me I need to do more. So I'm going to take the derivative of the top function and then the derivative of the bottom function. Okay, but remember, L'Hopital's rule, you're not doing like a giant quotient rule. You're keeping those functions totally separate. So we're going to retry the limit as x approaches 4. ln x, the derivative of ln x, I'm going to put it up here in the corner, of ln x is 1 over x. Okay, so when I take the derivative of ln x, I'm going to get 1 over x. ln of 4 is another kind of like that e thing, that's a constant. Okay, I don't know what the ln of 4 is, but I know that it's a number, and when I take the derivative of a number, I know I'm going to get 0. Okay, so on top, I have a 1 over x. On bottom, x minus 4, the derivative of x is just a 1, and then the derivative of minus 4, which is a constant, goes to 0. So that means really, I'm just looking at x approach 4 plugged into a 1 over x. Well, then it's going to be a 4. Okay. What do you think about that? Great. Okay, next one. We have the limit. As x approaches pi halves, we're going to plug it into the top first, which is 1 minus sine x. Then we're going to plug it into the bottom second, which is 1 plus cosine of 2x. So let's do this one first. So I would plug in my pi halves. I would have 1 minus sine of pi halves. Okay, then pi halves would be your thumb here. Hold your thumb down, signs all your fingers on the bottom. They're all on bottom. That means it's a 1. So I have 1 minus 1, which gives me 0. Check. L'Hopital's rule now on the bottom, we got to see if it applies. So I'm going to plug in my pi halves. So I would have 1 plus the cosine of 2 multiplied by pi halves is just going to be a pi. Think about that for a second. I already had a 2 in there, and then I'm multiplying that 2 by the pi halves. Those 2's are going to cancel. And then if you think about pi, that's right there on the x-axis on the unit circle. So you'd be on your pinky. All my fingers are above, which means it's 1. But because I'm at pi instead of 0, it's actually a negative 1. And 1 minus 1 is 0. Check. Which means L'Hopital's rule applies. And now remember too, just because L'Hopital's rule applies, it doesn't mean it's going to fix it. It just means that it'll tell you if it exists or not. So it exists if you get 0 over a number, that means it equals 0. It exists if you get a number, okay, but if you get a number over 0, remember that means does not exist because of the okay, no, and do more, okay? So let's do it. So we're reapplying the limit as x approaches pi halves. On top, I have 1 minus sine x. Well, the derivative of 1 is 0. The derivative of negative sine, snow cone. If I'm on negative sine, the derivative of that would be negative cosine. Then on the bottom, 1 plus cosine 2x, the derivative of 1 is 0. The derivative of cosine is negative sine. But it's a chain rule. It's not cosine x, it's cosine 2x. So that 2x is plugged inside the cosine. That means that I'll take the derivative and get negative sine of 2x, but then I'll still have to multiply by 2. So then we're going to plug in our pi halves here. So I have the negative cosine of pi halves over negative sine of 2 times pi halves would just be pi. And then I'm going to have to multiply that by 2. Cosine of pi halves would be your thumb. That's going to give you 0. Actually, I can just cancel out these negatives, right? Okay, but then on the bottom, the sine of pi, that's going to come out to be 0. So, okay, now look, I've already written it as this is 0 over 0. Okay, on the AP test, I would lose points for that. So what I'm going to do is just going to scribble it out. Okay, it's not the end of the world if you put it, as long as you don't leave it there. And then we're going to basically have to apply L'Hopital's rule again. So, getting out a little sticky note here. Okay, we're going to try the limit again. X approach pi halves. The derivative of negative cosine. Remember, I'm taking the derivatives at the top and the bottom now a second time. So negative cosine would get me back up at sine x. And then the derivative down here, if I'm on a negative sign, the derivative of negative sine is negative cosine x. But then, oops, hold on, 2x. Negative cosine 2x. But then I'm going to have to times by another 2 because of chain rule. So that means that this 2 in the back is now going to be a 4. And then I'm going to go about trying to plug those values in. So on top, I would have a sine of pi halves. On bottom, I would have a negative cosine of pi times 4. Okay, and then think about, where's that pi coming from? Well, I have a pi halves times a 2 in the 2x part. That cancels that out. Cosine of pi is -1, okay, which means that I have -1 times 4. And then pi halves, if I'm at 90 degrees, the top of that's going to come out to be +1. So I have 1 divided by -1 times 4, which is going to give me a 4. So I'm just going to put over here equals. Okay. So I guess we probably needed a little more room for that one, but maybe you didn't. Maybe you wrote small enough. Okay, we have 3 more examples left that we have to do. Then you have some extra practice problems on the back if you want to challenge yourself. And then the answers are here at the bottom so that you can check your work to those 4 questions. But if you don't want to do them, they're not really due. It's just good to practice. Okay. All right, so let's take a look at 10 through 12. This is how they test L'Hopital's rule most often. Okay, they're going to give you a giant table of death, and then they're going to give you a big, scary looking limit, and they're going to tell you that you just basically have to figure out what that limit is. Okay, so the first thing that I'm going to do when I see this set up on a problem is it is 99% of the time L'Hopital's rule. So you might as well just set those limits up separately, okay? Because we know how it's going to come out, right? So limit x approach 2 of 3x minus 6. Well, if I plug in a 2 to that, I'm going to have 3 times 2 minus 6, which is 6 minus 6, which is 0. Then I'm going to check the second limit, which is the limit of the bottom. I'm going to check the limit as x approaches 2 of 2 times f of 2x plus 2x. Well, when I plug this 2 into the middle here, that's going to be 2f of 4. Think about if you understand where that came from. I already had a 2x in here, and then I'm plugging a 2 into that spot. So that'd be 2 times f of 4 plus, and I'm also plugging that 2 in here. So 2 times 2 is going to be a plus 4. Then I look at my table for f of 4 and see f of 4 is 8. Which means that I have 2 times 8 plus 4, which is 16 plus 4, which is 20. That one didn't come out to be L'Hopital's rule. So then I would say, okay, well then my answer here would be 0 on top divided by 20 on bottom. 0 divided by 20, that's okay. It gives me 0. Okay. Let's try the next one. Now remember again, why did I not use L'Hopital's rule there? Because I didn't get 0 over 0. Okay, it's okay to get 0 on the top. Your answer is 0. No, you can't get 0 on the bottom. That means it doesn't exist. Okay, but if you get 0 over the 0, that's when you do more. Yeah. Okay, 2 more left. Next one, we're checking x approaching 2 of f of 3x minus 2x. So that's going to be f of 3 times 2 is going to be 6. Minus 2 times 2 is going to be 4. Then I come over here to my chart. F of 6 is -1. And -1 minus 4 is -5. Oh, so this is not going to be L'Hopital's rule either. That's okay though. Okay, I pulled these off of Delta Math. Clearly I should have thought this plan through a little bit better. X approach 2 down here would be 4x minus 2x squared. So I would have 4 times 2 minus 2 times 2 squared. 4 times 2 is 8. 2 squared is 4 times 2 is minus 8, which gives me 0. Now this is important. Look at which one came out to be 0. This time I got negative 5 on the top divided by 0 on the bottom. That's not a L'Hopital's rule, but the answer is not 0. It's a DNE. Okay, that doesn't make sense. You're not allowed to divide by 0. Okay, last one. Hopefully this one is 0 over 0 or I'm going to be really sad. Okay, so we're doing x approach 4. So I'm going to do the limit as x approaches 4 of the top, which is 2f of x minus 2. That's going to give me 2f of 4 minus 2. F of 4 is 8. 2 times 8 minus 2 is 16 minus 2, which is not 0. It came out to be 14. Okay, then on the other side, we would have done the limit as x approaches 4 of 2x squared plus 3x, which is 2 times 4 squared plus 3 times 4. 4 squared is 16 times 2 is 32. Add that to 3 times 4 is 12. 32 plus 12, that's going to give you 44. And so then as you can see, this one didn't even give you 0 on either part. So you would have 14 as your top divided by 44, which is your bottom. Now it does say simplest form to make sure that you reduce that. Those can both divide by 2. So that would be 7 over 22 for your answer there. Okay, well, I picked kind of some wonky problems off of Delta Math, I guess. The last 3 didn't even really work for L'Hopital's rule, but hopefully you get how to do it. Okay. I feel like I have to do like one of these practices just to, you know. Let's do number 14. Okay, I'm sorry. I told you it was the last one and now it wasn't. Okay, so we're doing limit as theta approaches 0. I'm going to do the top first, bottom second. Theta approaches 0 of 1 minus cosine theta. Well, that's going to be 1 minus cosine of 0. Cosine of 0 is 1. 1 minus 1 is 0. So the top limit came out to be 0. Now we're going to check and see if the bottom limit comes out to be 0. So I have the limit as theta approaches 0 of the bottom, which is 2 sine of theta squared. Okay, now remember, those are the same. They're written differently, but this and this are the exact same thing. Okay, one of them has the squared kind of tucked in, the other one has it out at the back, but either way, it's the same. So I'm plugging in 2 times the sine of 0 squared. Well, the sine of 0 is 0. 2 times 0 squared, gonna be 0. That means that I can use L'Hopital's rule here. So let's do it. Reapply the limit as x approaches 0, but then I'm gonna have to take the derivative of the top and the bottom separately. So if this is 1 minus cosine x, the derivative of snow cone. Okay, if I'm on negative cosine, that's going to pop me back up here to be at sine theta. Notice it's going to switch it to be positive. And then on the bottom, I'm going to look at this version because I think it looks nicer, but I'm going to have to do chain rule on this. So my outside function, I would do 2 times 2, which gives me a 4. Sine theta stays the same, but now it's just to the first power because I have to power it down 1. And then I have to multiply by the derivative of sine theta, which is a cosine theta. And then look what happened. Sine theta on top, sine theta on bottom. You know what to do. Cross them out. And then your answer is just 4 cosine theta. But then I can, of course, plug in the 0. Okay, then I go to plug in. Remember, cosine of 0 is 1. So that's 4 times 1. Suspicious. There's no 4 as an answer. That's because, bam, when you cancel that sign out, you got to leave something up there. Okay, so it's 1 over 4 cosine 0, which is 1 over 4, which is then a 4. Okay? But don't forget that chain rule. Okay? If it's sine of theta squared, you got to make sure you do chain rule around it. Okay? Good job. Very good job.